Swayam Prabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. Today I am going to talk about laser beam micromachining part 2. Acknowledgement same as for part 1. N.J. Basa who wrote a chapter to the book on micromachining. Advanced machining processes book. Syed Nadeem Akhtar PhD student, Benedict book. What we have done in the last lecture on laser beam micromachining: introduction to laser, introduction to laser production, characteristics of lasers. Then we discussed types of lasers and characteristics, specifically gas laser, solid laser, liquid laser, semiconductor lasers, and then this is LASER. And then we discussed other way of classifying lasers as nanosecond laser, femtosecond laser, picosecond laser, aximal laser, and so on. Theoretical analysis also we discussed about the laser beam machining and laser beam micromachining, in which analysis of LBM, theoretical calculations for calculating intensity, material removal rate, and depth of machining during LBM and LBMM. Working principle of laser beam machining and laser beam micromachining we discussed in the last lecture. We also discussed how it removes material during LBMM and LBM, interaction between laser beam and work material, and some effects of type of laser on the machined workpiece characteristics. Now what we are going to do in part 2, that is parametric analysis. Long pulse laser beam micromachining demerits are there, like adverse effects of long pulse laser beam. We have seen already in the earlier slides in the part 1 lecture what are the various demerits or defects caused by long pulse laser beam machining, and I had shown to you the photographic view and schematic views also. Damage to adjacent structures, delamination in case of composite materials, formation of recast layer, poor short to short reproducibility, material is removed by vaporization, and a lot of energy used in the melting material, which also wilds. This wilding ejects flux of the molten material away from the work zone. The ejected globules from the drops that fall back onto the surface and contaminate the sample, and they form as what is known as recast layer or debris on the machined surface, and they are highly undesirable. There are certain ways of removing them. I had discussed with you while discussing the nano finishing processes. Some of the nano finishing processes are efficient enough to remove the recast layer and globules. These droplets retain a fair amount of residual heat and may bind strongly to the sample. Removal of these contaminants may be difficult or impossible without damaging the target, but in some cases, yes, you can remove it. High heat melts an area that is much larger than the laser spot. Therefore, it is difficult to do very fine machining, because we have seen in the part 1 also that the temperature reaches in some cases as high as 8000 degrees centigrade. So this what is written over here is that heat affected zone and some melting outside the focused beam spot also takes place. Heat affected zone is another problem which causes mechanical stress and can create micro cracks on the machine surface. You can see here, these are the molten material which has been redeposited in creating all kind of problem on the machine surface. You can clearly see over here, and these are all solidified molten material. This is the recast layer, globules are there, and heat affected zone is there. Heat diffusion affects the large zone around the machining spot. A zone referred to as the heat affected zone or HAZ abbreviated. The heating and subsequent cooling waves propagating through the heat affected zone cause mechanical stress, and this is highly undesirable and may create micro cracks in the surrounding material, and again they weaken the component and reduce the life of the component. These defects are frozen in the structure when the material cools, and the subsequent use, these cracks may propagate deep into the bulk of the material and cause premature device failure. So this is another big problem, because these micro cracks, they expand in the material and later on make it to premature device failure. Recast layer and delamination, a closely associated phenomena, is the formation of recast layer of material around the machine feature. We have already seen pictures for this. This resolidified material often has a physical and or chemical structure that is very different from the unmelted material, and this also has very high hardness compared to the parent material. This recast layer may be adhered, mechanically weak, and must often be removed before really putting the part in the assembly, sub-assembly, or making the use of the component. This has to be removed. Heat affected or heat diffusion is sometimes associated with the formation of surface shock waves. These shock waves can damage nearby device structures or delaminate multi-layer materials. Amplitude of the shock wave varies with the material being processed. It is generally true that more the energy deposited in the micromachining process, stronger is the associated shock wave, and it has its own problems. Process parameters, some of them I have shown to you already. Thermal properties of the workpiece material, mechanical properties of the workpiece material, optical properties, physical and chemical structure, and initial temperature of the material, workpiece material, radiation, pulse energy, pulse duration, fluence, repetition rate, and beam intensity profile. These are the parameters which affect in some form or other the process performance of laser beam machining and laser beam micromachining. Optical setup, angular divergence of the laser beam or laser waves, irradiated spot size, mask area, this is very important, mask area, demagnification factor, beam compression, focal length, and others are assist gas, because I have shown to you a picture in the part 1 that where gas is assisting the laser beam micromachining process. So which gas you are using and what are the characteristics of the gas, what is the velocity of the gas flow, etc. affect the process performance, cutting speed, and continuous wave or pulsed wave, power supply, which one is you are using, that also affects the performance of the process. Low pulse frequency, high peak power or high peak energy density, gas and nozzle angle, optimum cutting speed, high pulse width, all of them affect the process performance in some form or other. And to get high material removal rate, you can see here the relationship fluence in joules per centimeter square, and this is the ablation rate, that is nothing but removal of the material in terms of micrometer per pulse. And you can see as fluence is increasing, the abluence rate is continuously increasing. This is 5 millimeter per second, 10 millimeter per second and 20 millimeter per second as the feed. Now you can see here fluence and ablation rate again for different speeds. The ablation rates, material removal rates of laser micromachining versus fluence, laser fluence for aspheric wafer. This is for aspheric wafers and this is for silicon wafer with different cutting speed. So you can see RA, surface roughness value, how it is affected by the feed rate in millimeter per second, and this is power 700, 900, 1100, 1300. So you can see clearly how this is varying to some extent, minimum or increasing more or less constantly with the feed rate. But what happens after a certain feed rate, you cannot predict from this graph. Effect of machining time on the depth of machining. Here you can see it. I is missing over here, machining. So thickness, as the time is increasing, machine thickness is increasing, and after a certain time it becomes asymptotic over here. Now pulse energy, as pulse energy is increasing, joules per pulse, and time taken is decreasing. Time taken for machining is decreasing. Theoretical analysis, acrylic, you can see here depth of cut for laser speed. As laser speed is increasing, depth of cut is decreasing because time available for the material to be removed by melting and or vaporization is decreasing. That's why you can see the depth of cut is continuously decreasing and it is becoming asymptotic. And as the power is increasing, depth of cut is also increasing. This is for 6 watts, 24 watts and 60 watts. And experimental results again, depth of cut, laser speed, and you can see here again similar kind of the behavior is obtained experimentally also. Cutting acrylic plastic board PMMA for variation of laser depth of cut with laser speed for different laser power. These are the different laser powers. Depth of cut does not vary linearly with moving speed. As you can see, it starts decreasing and then it becomes asymptotic. You can see over here, and there also it is more or less the same behavior. Any increase in laser power will increase the depth of cut. That you can see behavior here also, because this is higher, that is for 60 watt, and this is minimum for 6 watt. When it is a deep cut, depth of cut is decreased by blocking effect. Properties of the material fluence, the blocking effect. Cutting fine wood, you can see here different results are given. This is for the rubber, and then there are for other pine wood is there, particle board is there, and so on. When workpiece moving speed is greater than approximately 25 millimeter per second, the depth of cut remains unchanged. You can see here this is the 25 millimeter per second as the laser speed, and after this the depth of cut becomes more or less constant. Among the 3 materials given in the figure, that is this figure, the depth of cut for rubber is the lowest, that is given over here, and highest is for pine board. For plastic board, if the depth of cut exceeds over 20 millimeter, a more powerful laser is needed. Here velocity of assist gas at the nozzle exit, that you can see over here, and this is the cut depth, and after a certain velocity of the assist gas, the change in depth of cut is almost zero or negligible, that you can see here from all these graphs. This graph represents the variation in the cut depth with assist gas velocity at the nozzle exit, that you can see over here. The curves below, the curve shows zero cut depth for zero gas velocity, that is over here, you can see at this particular point, and then attains constant values. At higher scanning speed, the maximum cut depth is achieved, that is somewhere here you can see, and here is the zero. Is achieved at higher gas velocity through still less than the critical speed, because the gas jet interacts with the workpiece for shorter duration. You can see here scanning velocity, and there is a critical speed beyond which there is no change in the cut depth. The graph shows the variation in the cut depth with the scanning velocity, that is what is shown over here, and then the cut depth drops sharply for higher scanning speed, that you can see over here. This is dropping, and because the laser material interaction time decreases, because as the scanning velocity is increasing, the time for the laser to interact with the workpiece material at a point decreases. Therefore, laser beam deposits less energy on the workpiece when the beam is scanned at the higher speed. So, it is very obvious with this explanation that why this increase in scanning velocity, the cut depth is decreasing, and it is becoming almost asymptotic beyond a certain point. There are some more results. Assist gas velocity, nozzle dip, that we have seen all here. This graph represents the variation in the kerf width with assist gas velocity. Kerf width is increasing up to certain point, then after that there is no change, almost no change. So, it says this graph represents the variation in the kerf width which with assist gas velocity at the nozzle exit, and I have already explained you what is the kerf width in the part 1 lecture. The kerf width rises sharply. I can show you here again. See, this is the workpiece, and this is the machined area, then this is known as kerf width. The kerf width rises sharply as the gas velocity increases, that is what you can see here. It is increasing in this particular direction, and then attains a constant value. At higher scanning speed, this you can see here, this is beyond this, it is almost constant. At higher scanning speed, the maximum kerf width is achieved at higher gas velocity, because the gas jet interacts with the workpiece for shorter duration. You can see a kerf width with laser scanning velocity. Graph between kerf width and laser scanning velocity, you can see here kerf width decreases as the scanning velocity increases. So, this is decreasing in this direction because scanning velocity is increasing in this direction, because of less energy deposition or less time available for energy for deposition on the workpiece, and raising the temperature on the workpiece at higher scanning speed. That means the speed with which laser beam is scanning the workpiece surface. Conclusion: for this particular part, models for melt and cut depth and kerf width are presented for laser grooving and cutting applications. These models I have discussed in the part 1, and I have given the results, experimental and theoretical, in part 2. Experimental data for both cut depth and kerf width validate the model predictions that is presented in part 2, and we have just now seen those pictures or those graphs, 2D graphs. Now let us see laser beam micromachining process characteristics, some more details, some salient features of the LBM and LVMM process. Can machine tough glass optically transparent material, we have seen it earlier also. Can machine in inaccessible areas, because there is nothing like a hard or physical tool, it is rather a beam which should reach through inaccessible areas to the location where machining is to be done. So it is very easy to machine in inaccessible areas, not competitive with conventional techniques, because there is a high capital cost and high operating cost of laser beam micromachining. In future, commonly used system on shop floor, this may become so popular that it may be commonly used on shop floor, because researchers are continuously working hard to enhance its performance and efficiency. The ruby rod is less efficient at high temperature, cooling is required. Expelled material, that is the droplets in the form of droplets in the laser beam path, they continue to absorb the energy. Whatever droplets are coming in the laser path, they continue to absorb the energy from the laser beam. Laser beam machine component has low fatigue strength. It may be due to micro cracks and thermal residual stresses. Thickness of heat affected zone depends upon feed rate, gas pressure, nozzle tip distance, and TD means nozzle tip distance, and gas nozzle diameter. No mechanical forces act on the workpiece, we have already seen. LBM cannot be applied to the material having high thermal conductivity and high reflectivity. Please note it very carefully, this is a very important characteristic, that LBM cannot be used for machining those materials which have high thermal conductivity and high reflectivity. Some of them are like aluminum, because in some cases a table for holding the workpiece is made of aluminum. Copper is also more or less the same, and so on. Machining table is made of aluminum material in some cases. LBM is quite inefficient system, because I can tell you in some cases, or rather than in many cases, efficiency of laser beam machining and laser beam micromachining is less than 5%, which has improved now with technological development. So people are still working hard to enhance its efficiency. Efficiency is as low as 1% or so, because there are so many losses during the production of laser, during the maintaining of the house rooms for this laser production, and there is a lot of loss of the heat conduction, convection, and other ways I will show you in other transparency. LVMM process characteristics, let us see this. LV laser beam incident power, some of the power goes into by reflection losses, some goes by scattering losses, and some part of it is absorbed by the metal or material surface which is being machined. Now whatever is absorbed, you can see there is a thermal diffusion. So thermal diffusion loss is there, liquefaction of material is there, which is again absorbing the latent heat of the melting. Then there is a vaporization of the material, so material removed by vaporization finally, but removal of material by high pressure of vapor is also there, and then there are the radiation losses. So you can see here there are various ways through which you are losing the energy, thermal energy, and that's why the efficiency of this laser beam machining process is so less, normally less than 5%, but nowadays it might have improved. A part of the laser beam energy is lost due to reflection and scattering from the workpiece, and some part of it is absorbed by the workpiece and which is used for and for various ways, and lot of losses are there again. You can see here the case of laser beam drilling. You are drilling a hole with the laser beam and you can see the shape you are obtaining by laser beam. At the entry it is a much larger diameter than at the bottom, and this is the recast layer kind of the thing. Erosion front, molten layer is there. Once it gets redeposited, adhere to the machined surface, then you will call it as a recast layer. And here is the heat affected zone. You can see grooving using the laser beam. Again same phenomena is taking place over here. This is another way, laser beam is there, scanning is in this direction, then conduction of the heat, molten layer is there, ejection of molten material, that is over here, and some evaporation takes place. This is little important one. You can see the characteristics of the machined hole by laser beam micromachining. You can see here, A is the mid-span diameter, this is the mid-span diameter, and B is the recast layer. You can see over here, B is the recast layers, D is the hole depth, this is the hole depth, this is the recast layer, then E is the inlet diameter, that is the inlet diameter, and C is the outlet diameter, G is the surface debris thickness, that is shown over here, G surface thickness, and then phi is the inlet cone angle, and this is the inlet cone angle, and alpha is the taper angle. So you can see the characteristics of the drilled hole by laser beam micromachining and laser beam machining. Applications of laser beam material processing. Application of laser material processing, there can be involving change of phase or state, involving no phase change. In change of phase involving solid vapor, solid turns to the vapor, that is direct evaporation, solid turns to the liquid. You can see by this part machining, that involves cutting, drilling, etc., deposition, coating, laser spectroscopy, laser assisted purification. When solid is converting into liquid, you can have the joining like welding, brazing, surface alloying or cladding, rapid prototype, reclamation, and then involving no phase change, solid to solid. Surface hardening, bending or forming, semiconductor annealing, shocking, short pinning, because they are solid to solid, so there is no change in the status of the solid over there. You can see here what are the kind of the operations that can be performed. We are familiar with them, like forming, bending, straightening, manufacturing, coloring, deposition, rapid prototyping, they can be done. Joining of the material by welding, brazing, soldering, sintering, etc. Then machining you can perform like cutting, drilling, scribing, marking, cleaning, etc. These are the different kinds of the operation that can be performed by laser beam machining and laser beam micromachining. And then surface engineering, surface alloying, cladding, surface melting, remelting, surface amorphization, surface hardening and shrinking. So you can see here in this particular slide that various kinds of the operations can be performed by LBMM and LBM processes. Further applications, laser machining has significant applications in the automobile engineering, aerospace engineering and electronics industry for cutting, drilling, milling, etc. Nowadays CO2 and Nd:Arc laser and excimer laser are used for most industrial laser applications like heat treatment, welding, ablation or cutting of plastics, glasses, ceramics, semiconductors and metals. Please note it carefully, all kinds of materials are being machined or cut by laser beam machining. Doesn't matter they are electrically conducting, electrically non-conducting, magnetic, non-magnetic, having high thermal conductivity, low thermal conductivity. Material deposition, etching with chemical assist, that is laser assisted chemical etching, laser enhanced jet plating and etching, lithography, surgery and photopolymerization. So there are so many applications of laser beam machining. I will just quickly go through them without much description. In drilling operations, workpiece is placed at or near the focal point of laser beam, and the mechanism of material removal is melting and vaporization. We have already seen this. Drilled hole diameter varies in the range of 0.125 to 1.25 millimeter. Please note it, when you are drilling such a big hole like 1.25 millimeter, it becomes difficult to include it in micromachining because it is greater than 1 millimeter. The hole drilled is normally tapered, having low degree of roughness. It almost always gives recast layered walls. We have seen what is recast layer. The thickness of the heat affected zone varies like this, and the diameter repeatability varies within plus minus 0.025 millimeter, that is 25 micron, or plus minus 10% of the diameter, whichever is greater. Now in cutting, laser side holes are normally cut. Large side holes are normally cut, trepaned rather than drilled, because you cannot have that large size of the laser beam. No mechanical forces act during LBM, hence high speed cutting is possible for most of the time, and gas jet assist clearing the cut material during LBM. We have already seen in part 1 how the gas jet is supplied to assist the laser beam machining and laser beam micromachining. Argon is good for cutting edges. Argon material, argon gas is used, then it gives good cutting edges. Oxygen for oxidizable material gives higher cutting speed, but oxidized edges and larger heat affected zone are obtained. So when you are using oxygen, there are some advantages and some disadvantages also. Production of the cut shapes, through shapes, not blind. You can use CNC contour cutting. I have already mentioned that laser beam should be assisted with the CNC machine so that everything is done in a normal and proper way. Any programmable shape can be machined. Production of good quality blind feature is normally difficult. You can do it with the help of CNC machine a little better. Large size through features are possible by trepanning operation only. Optomechanical sweeping of the beam along the desired path is done using CNC feature of the laser beam machine. For machining cutting a small feature, the cycle time is a few seconds only, so that you have to really design it well in advance after knowing what is the material removal rate with these machining parameters. 3D cutting using laser beam machining and laser beam micro machining is possible, and you can see here this is the turning and threading using the two laser beam A and beam B, and here is the material removed from this part. This is the thread being produced. So this part, from this part material is being removed, that is this one. So here you can have milling operation like two lasers A and B, and this is the material that is being removed. So all kind of operations can be performed by manipulating with the relative motion between the beam and the workpiece, and that's why I mentioned that CNC machines can make you a very good 3D component by laser beam machining and laser beam micro machining. Marking can be done very easily with the help of laser beam micro machining, and it is being done in many industries these days by laser beam. You can see these are the letters marked over here. This is the another one, different letter numbers and X, Y, Z are marked. This is the pen where marking has been done by the laser beam micro machining, this one. So LBMM is an efficient process to make letters, numerals and symbols on metal and non-metal that are given here. This is on the metal, this is on the non-metals. Pulsating laser system and computer controlled beam scanning system enhances the efficiency of the LBM. Blind groove features of very small depth, 5 micron to 250 micron, are feasible to make with appropriate machining parameters. For high quality marking, laser beam lasts for nanoseconds, not microseconds, nanoseconds. Microcomputer is used to control position and timing of laser beam. 30 characters per second, which is quite large. 30 characters per second is the normal speed of the system. Machining of submicron features, as you can see here, submicron features can be machined with the help of this. The unique combination of multi-photon absorption and saturated avalanche ionization provided by ultra-fast laser pulses makes it possible to machine materials on dimensions much smaller than 1 micron. So you can go for machining in the nano range, not only micro range. If the wavelength of the light is about 0.5 micron, that is 500 nanometer, then the smallest spot we can create is about 500 nanometer, that is 0.5 micron. This figure shows how an ultra fast laser pulse can create features substantially below that of the central wavelength of the laser pulse itself. First, we focus the ultra fast laser on a spot with a profile which has a peak intensity in the center of the beam. You can see here, this is the center of the beam, and peak intensity is in the center of the peak over here and here. Center of the beam, and it smoothly decreases rapidly outward from the center, that is a Gaussian spot. If we adjust the intensity of the laser spot on the surface of the material so that just the peak of the beam is above the threshold, then we will remove material only in that very limited area. Laser ablation of diamond. It is extremely difficult to cut or machine the diamond. Diamond wire drawing die. This die is made with diamond with 50 micron size. Diamond is difficult to machine because it is transparent in a wide wavelength range. At high power densities, however, the diamond is transited into graphite, which absorbs the laser power and is removed by ablation subsequently, because it is very difficult to drill a hole in the diamond. So diamond machining is currently done by microsecond pulse Nd:Arc laser and nanosecond pulse excimer laser. Now this is very interesting application. Laser cut stent-like micro pattern in miniature stainless steel tube. You can see here, this is the stainless steel tube, and miniature features are created. They are shown over here with this arrows, and these are the miniature features created over here. And this is done by laser beam machining. Then laser drilled hole, not circular, non-circular holes are drilled, diameter around 15 micrometer, patterned in polyurethane tube. This is the polyurethane tube. Circular holes are also there, and square holes are also there, and much smaller holes are also here, as you can see over here. Inkjet nozzle drilling. You can see these are the ones. Inkjet pointers are widely used, consist of an array of small orifices with precisely defined diameter and taper, each located on top of a channel with resistor heater. Small bubbles, these are the inkjet holes. Small bubbles are formed when the ink is heated, ejecting small drops out of the nozzle. Depending on the design, up to 300 holes have to be drilled simultaneously in a 0.5 mm into 15 mm area. About 300 pulses are applied to obtain 55 micron holes with 27-degree taper. So you are able to achieve the tapered, very small micro holes. The total drilling time is about 1 second using a 300 Hz KRF laser. This is the type of the laser. Laser drilling for medical applications, very interesting. These are some of the holes drilled for laser medical applications. Copper vapor lasers are mainly used to drill, cut and micromill materials with a thickness up to 1.5 millimeter in metal, silicon, diamond, ceramics and polymers. Such holes are found in medical flow controller, microelectronic contacts and micro medical filters shown in the figure. Holes are also used to make plastics breathe able, to calibrate leak testers and to perforate foils. This is very interesting application here. Surface cleaning of art. Partially cleaned left side. This is the old art which is cleaned partially over here and then fully cleaned on the right side. You can see the clear difference between the dirty or uncleaned art and cleaned art. It makes a lot of difference, and this cleaning has been done with the help of laser beam. Impressive results were achieved in the restoration of painting by 20 nanosecond KRF axial laser pulses. The ablation depth per pulse is about 1 micrometer. Process monitoring of the laser induced plasma by real time. Spectroscopy allows the precise control of the ablation depth and identification of the different layers. So you can clearly see the difference between clean surface or clean art or clean painting and unclean painting. You can see here 5-axis machining of automobile component with the help of laser. This is the automobile component and they are 5-axis machining, X, Y, Z, A and means A and V rotation. Laser cutting of wood. Here you are cutting the wood with the help of the laser beam and different kind of the features are creating over here on the board, and it takes few seconds to really cut it and make the feature. Feature creation on a paper. This is a piece of paper where different features are being created with the help of the laser. So there is a relative motion between the laser beam and the workpiece surface. Micro products, you can see here internal gear, external gears, micro gears rather, and here is the gear by micro molding, 500 micron size, 300 micron size. This is the green, and this is the enlarged view of this tooth that you can see over here. This is the tooth, enlarged view of this particular tooth. Machine microstructures, you can see here simple structure machine with CO2 laser, microfluidic structure. These are made on this transparent material. Here are the 50 micron holes, percussion drill with KRF, then cross section of micro channels that are machined over here. Then micro features made in polyester with KRF. You can see different kinds of features created with the help of lasers. And then micro features made in polyester. Again, polyester, you can see the 3D features are created over here in one go. Then you can see on the right side metal melt, this one melt material, and in the middle here it is the feature created. This is the another one, left side PVT photolytic ablation over here. So what I am trying to tell here is about different types of material you can make use of laser beam machining and laser beam micro machining. Now this is the direct write and mask projection using laser beam micro machining. This becomes the one-step process for making the feature on the workpiece. Mask projection technique. Here you are projection lens is there, sample is there, mask is there, it is subjected for that, field lens is there. So with the help of laser you are preparing the mask where these are the material has been removed from here, right? And so laser beam is coming over there, and this is the sample, this is the laser beam coming through the mask, and it will be removing the material from this part where this laser beam is coming. And you can see from all the three locations the ablated material over here, here and here material has been removed, because mask is kept at the rest of the places. So it is not allowing to pass this laser only from the area where from mask has been removed. So advantage is mask is remote, no debris damage, demagnification allows larger mask features, demagnification allows lower fluence at the mask, mask can be moved independently so that you can create different types of the features on the sample. Incident light, you can see different applications over here also, that is this bigger laser beam is coming over here, you can create the features over here. Here transparent plate is there, opaque elements are there, so you can have different kind of application. Gray scale masks are there, and these are the kind of the features that have been created. Width and density modulation, this is the feature I have shown you in the earlier case also, and this is how incident light is coming. Phase shifting, there is no mask, then through this light will come and create the feature. Static mask projection, depth depends on exposure time. So you can see here it is the 3D feature, and steps are being created, and by having different masks at different locations you can create these steps by controlling the exposure time. Again complicated but useful features are created over here with the help of the mask projection. This is another one, again 3D, complicated features are created here, again same one which we have seen earlier also. So workpiece dragging, channel section depends on mask profile, whatever is the mask profile, based on that you are removing the material and you are creating these features. Mask dragging, slope depends on dragging speed. So this is what you are getting based on the dragging of the laser beam or moving of this workpiece and keeping the laser stationary, you can create these kind of the features. Very nice features created over here. Synchronized overlay scanning, this is the another one. You can create these kind of the channel, uniform channels. This is a complicated one, kind of features or textures you can create with the help of this particular laser beam. And then another one, vertical walls kind of the things have been created, and you can see the gap between the two and wall thicknesses. Conclusion: laser micromachining is now established microfabrication process for manufacturing many device structures. Some of them we have already seen in two presentations. With the correct choice of laser and processing parameters, virtually any material can be laser micromachined with submicron precision. Note it here very carefully. I have many times mentioned that you must optimize to have the best performance from the process. Doesn't matter whether laser beam or electric shaft or electrochemical machining and so on. Optimization is very much needed. Thank you very much.